put more devices on the surface. Basically, the law says that every 18 months you double the amount of devices you can put in the center. Now there is a problem. As you make things smaller, they start to fail. Silicon is no longer working because it starts to leak. The dielectric layer, which is what we're going to focus on, because you're shrinking the whole device, so your dielectric layer has to keep going smaller and thinner and thinner and thinner. Now, at about 32 nanometer, you start to have a lot of defects in this layer, which starts to leak. And if you have a device that is leaking, it fails. So what is the solution? The solution is to look for a different material, and that's what the chemists have done. Basically, what you're seeing here is that the molecules in red, these are normal organic molecules, and we have them since, I don't know, 1,000 years. But we recently discovered that if you align these molecules standing up like that, which we can do with nanotechnology very simply, their dielectric constant increases with the length of the chain, this alkyl chain. So basically the idea, and this is the future of electronics, is to actually use organic molecules as devices. What you're seeing on the left here is a measurement of the number of carbon atoms in the chain, and the threshold voltage, as you can see, the more you increase the number of carbon atoms, the more the threshold goes, which is basically the length of this is 10 nanometers. So at a length of 10 nanometers, I can do the performance of the silicon dioxide dielectric layer that I can achieve at 50 nanometers thickness. So by just changing the material, the ability to control it, I can actually make a device that functions better than the technology we had 4 years ago at a much fraction of the size. The second thing about electronics is flexible electronics. Now, this approach here, one thing you have to know about nanotechnology is that nanotechnology is not, I mean, it's a new approach to all problems, but you also got a lot of application of ideas that we had before. The idea here is very simple. How to make a flexible electronics. What you can see on the left, this is the typical, up on the top, this is a very typical way of building a device. Using photolithography and printing technology, you can actually have your device built on the surface. The difference here is that we have a polymer, plastic material basically, that we stretch, we put it down on the device. The device is transformed or transferred to the polymer. We let the polymer relax. And as it relaxes, the device is wavy. Now this waviness allows us, as you can see on the left, to print a whole circuit and still the polymers. So this is one way of achieving new devices that are flexible. Now I'm going to shift to water applications. What you're seeing here is a life straw. Unfortunately, I have one, but I forgot it. It's a life straw. It's a device that is that big, that thin. It costs $3.50, and it can provide you with fresh water for an entire year per 1 product. $3.50. That's about 18 Egyptian pounds. 700 liters of water are fresh, clean water. No bacteria, no viruses, no impurities in it. And it costs you $3.50. Now, the company that is selling this are only selling it to first responders, to the Red Cross, the Red Crescent, the United Nations. They don't sell it publicly because they are afraid that the armies will have something like this and actually use it for different purposes. Now, companies are selling the same technology commercially, and they sell something like this for over $200. And this is a very important message. Using nanotechnology is not expensive, because you can build something like this for $3.50. It costs you $3.50. But if you buy it commercially, it's going to cost you $200. And this is why nanotechnology is very important for us in the developing country to work on it today, because when we have the know-how, it's going to be a lot cheaper for us to build something like this. Continuing with the theme of water, I'm going to show you some of the innovation. These tubes are made actually of carbon nanotubes. It's a mesh of carbon material, very strong, very simple, and it actually can kill bacteria, kill viruses, and clean up pollution. Now, this is another approach. This is actually done about 2 years ago, where you have a full tube as a filter made out of carbon nanotube. If you look here at this, the whole thing here, this area, is actually made out of carbon nanotubes. The advantage here, again, you don't need a battery, you don't need power, you just put the water in and it will come from the outside clean. There are a number of very different technologies in this, and this is actually using something electrical engineers and electronics engineers know very well, which is lithography, where you can actually see what you see in the circles there. Again, it's for carbon nanotubes sticking out through silicon carbide film, and it filters water. This is very efficient, but it's extremely expensive because the way it is fabricated is based on the electronics industry. This is how the filters look like if you close in, and what you're seeing on the left side, these white dots are bacteria. And as you can see, the carbon nanotubes are holding all the bacteria in them, and eventually they kill them. So again, you get fresh water coming easily. These are some statistics of how a nano-fabricated water filter or water membrane compares to a normal. The energy consumption is 20% less if you have to use for industrial scale. The water production is 170 more than a normal membrane. And the reduction in the plant size, where you fabricate these membranes, is 40% reduction. Now I'm going to move into something more relevant to us. Staying with the theme of water, but moving it into agriculture. Now, almost 95% of Egyptian land is deserts. And one of the biggest problems in irrigating the desert is the water. The water slips through the sand very fast. Now, there was old ideas 20 years ago is to put a bed of plastic sheets under the sand so it holds the water. Now, this technology has a problem because the water stays above the plastic and the plant itself grows. So you're actually not getting the benefit. Now, this is, what you see here is a bunch of sand in somebody's hand, treated with some nanomaterials, and on top of it, a drop of normal water. And as you can see, the water is not sipping through the sand. It will eventually go down through the sand. It will eventually thick through the sand. But it's going to be very, very slow, which gives a huge amount of time for the plant to actually capture the water. Now, this technology at the moment is not economical for Egypt. It's very expensive. But it will come down in price. And when this happens, and it will happen very soon, it will be possible to irrigate the entire desert much simpler with a lot of easier technology. Now, I'm moving a little bit from the water to the agriculture. Does anybody know what is organic food? Does anybody buy organic vegetables? Anybody know what's organic food? Somebody? What is organic food? Your colleague actually correct me. Organic food is a food that is not treated with pesticides and chemicals. Does anybody know why is that better than normal food? And so it's health surplus. Exactly. Now, why is that very expensive? Does anybody know why having organic food is very expensive? To some extent, yes. Your colleague answered because fertilizers make the food, the production yield is higher. But it's actually a different problem. In addition to that, if you have a flatbed, an acre, and you try to aggregate to